In this video, we want to take a look at the notion of linear independence. It is probably among the most important topics here for the rest of this course, so it will behoove you to make sure you understand the definition here. Okay? And actually, I'm going to give you two definitions because different textbooks use different definitions. They're equivalent, and we'll prove they're equivalent. I find it curious that the textbook we're using for this course in previous versions use what I'm calling definition one, and the current version uses definition two. Um, Whatever, either way, they prove that the two are equivalent, and we will do so here. So here's the notion of linearly independent. So suppose S is a set of vectors in a vector space V. And notice that this set isn't just any old set, it's a finite set. There's not infinitely many things in S. There's vector 1, vector 2, all the way up to vector n. Finitely many vectors, right? We will say that S is linearly independent if the only coefficients satisfying this equation are when all of those coefficients are equal to 0, right? So k1 v1 plus k2 v2 plus all the way up to kn vn is a linear combination of the things in this set S. We want them to add up to the 0 vector. Now clearly, if k1, k2 up to kn are all equal to 0, then this will add up to the 0 vector. The question is there any other way? And if the answer is no, there's not any other way, that if the only way is that all of the coefficients here are 0, then we say that that the vectors are linearly independent, or we say that the set of vectors is linearly independent. We'll actually say both. This is the definition I'm used to. It's what our textbook used to do, but now the latest version gives the following definition. If S is the set of vectors v1, v2 up to vn, this is a set of vectors in the vector space V, then we say that S is linearly independent if no vector in S can be written as a linear combination of the other vectors in S. Okay. This is not saying the same thing, but it turns out they're equal to each other. Okay. Before we do the proof of that they're being equal to each other, let me just say that if S is a set of vectors, same setup here, if it is not linearly independent, then we would call it linearly dependent. So if you have a set of vectors, it's either going to be independent or dependent. Okay. Now, the theorem here is that definitions 1 and 2 are equivalent. That is, if you know one is true, then the other is true. If you know the other is true, then the first is true. Okay. And we will give a proof of that. Suppose you've got this linear combination k1 v1 plus k2 v2 plus kn vn equaling the 0 vector, so that the k's are not all 0, right? What could happen if you had one when they're not all 0? Well, without loss of generality, that's what WOLOG means, I'm going to assume that it's the k1 that's not equal to 0. If it wasn't k1, then I could just reorder my set and take whatever one isn't, whatever of the k's is not equal to 0, take that same v and move it around so it's the first one. Addition is commutative. It doesn't matter what order you do these things. So without loss of generality, I'm just going to assume it's the k1 that's not equal to 0. Okay. So what I'm going to do is I'm going to take this equation and move everything over to the other side except for the k1v1. So k1v1 is minus k2v2 minus k3v3 and so on all the way up to minus kn vn. Okay. Notice, since k1 is not equal to 0, I can divide both sides now by k1. Multiply by 1 over k1, whatever you want to think of it as. And what I end up with is that v1 is a linear combination of these others, right? So what I've just shown here is that if there is a way of getting this to add up to 0 without them all being equal to 0, without the k's, essentially this is if you don't have definition 1, then you don't have definition 2, right? So I'm sort of proving the converse. Actually, no, I'm proving the contrapositive, right? This is that I prove that if not definition 1, then not definition 2, which implies that if definition 2 is true, then definition 1 must be true. So if you have a way of doing this without all zeros, then you can write one of them as a linear combination of the others. Conversely, if you have one written as a linear combination of the others, so if you don't have definition 2, then just slide everything over to the other side. You got v1 minus k2v2 minus k3v3 all the way up to minus kn vn would equal the zero vector. And this would be a linear combination of the v's adding up to 0. And I know that all the coefficients are not equal to 0 because the one in front of the v1 is a 1. That's not 0. So this is saying that if you don't have definition 2, you don't have definition 1, right? So rather than showing that 1 implies 2 and 2 implies 1, I show that not 1 implies not 2 and not 2 implies not 1, but either way, they're either both true or they're both false. Okay. So I really think of them interchangeably depending on what I'm doing, right? Notice with just two vectors, if I have two vectors that are pointing in the same direction, then one's a little bit longer than the other maybe, but you just have to take one and scale it up. So this k1 v1 plus k2 v2 equaling 0 only would have two things in it, or this would just be that v1 is some constant times v2 and you wouldn't have all the rest of it, right? So in a case like this where the two vectors are pointing in the same direction, they're not independent, they are linearly dependent, right? One is a scalar multiple of the other. However, if they're pointing in different directions, then it turns out they will be linearly independent, right? You can't write this one as a scalar multiple of that one. Right? We'll look at special cases here in a subsequent video. I want to do just a couple of examples written down here. So let's look in R3. I've got the vector 1, 2, 3, 4, 5, 6, 7, 8, 9. So three vectors in R3, and the question is, are they dependent or independent? Sometimes it's obvious. Sometimes you can just look and say, oh, if I multiply this one by 2 and add that one on, I'll get this one, right? And if that's the case, if you can see that clearly one is a linear combination of the other ones, then you know dependent. However, it's maybe not immediately obvious. It certainly isn't to me whether this is any one is a linear combination of the others. So what I tend to check is I tend to use what I call definition 1 and saying take a linear combination of all three of them, k1 times the first one plus k2 times the second plus k3 times the third, and set that equal to 0. That should be a 0 vector right there. Okay, this is the 0 vector. The thing is, since I'm in R3 now, this one vector equation is actually three real number equations, because if this is going to add up to the 0 vector, right, that's the 0 vector, then the first components have to add up to 0, the second components have to add up to 0, the third components have to add up to 0. I get three equations, three real number equations. So the first components would be 1 times k1 plus 4 times k2 plus 7 times k3. That has to be 0. Second components, 2 times k1 plus 5 times k2 plus 8 times k3. That's got to be 0. And third components, 3 times k1 plus 4 times k2 plus 9 times k3. That has to be 0. I now have a system of three linear equations and three unknowns, k1, k2, and k3. I know how to handle those things, right? We did that earlier in the course. And I know some things about that. One is, a couple of things. I see this is a homogeneous system because these are all zeros right here. So I know that there's a solution because 0, 0, 0 is a solution. The question is, are there any others? Well, since it's a square system, same number of columns as, same number of equations as variables, then I know that the coefficient matrix, if I take the determinant of the coefficient matrix and it's equal to 0, that means, well, if it's not equal to 0, it means there's a unique solution. And if it's equal to 0, it means that either there's no solutions or there's infinitely many. But since I already know there has to be one, it can't be no solutions. So there must be infinitely many solutions. And if there's infinitely many solutions, there's at least one of them that doesn't have them all equal to 0. Right? In fact, all of them except one. So the system has infinitely many solutions, and the set of vectors is linearly dependent, right? That there is a way to find k1, k2, and k3 um, to make this equal to 0. Just use the techniques from the beginning of the class. I don't need to do it here. Right? Now here's a slight change. So the first example was 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 1, 2, 3, 4, 5, 6, 7, 8, 10. And so with exactly the same setup, take a look at this linear combination. Does it equal? Again, that should be the 0 vector. And the three equations are just slightly different. There should be a 10 here instead of a 9. Let's see if we... All right, this all looks better now. We got a 10 there. We got a 0 vector and a 10 right here. The coefficient matrix now looks like this. If I take the determinant, it is not equal to 0, which tells me this system has a unique solution. And I know what that unique solution is. It's when k1, k2, and k3 are all equal to 0. So the only way that I can get this thing to add up to 0 is if k1, k2, and k3 are equal to 0, and hence those three vectors are independent, right? Notice the difference between, I got three vectors here, my two fingers and my thumb, right? And I've got them lined up, or trying to have them lined up, so that they're all kind of in the same plane. Those three vectors are linearly dependent. But as soon as they're now not all in the same plane, so two of them, of course, would be in one plane, and two of them would be in another plane, and the other two would be in another plane, but they're not all three lying in the same plane like that. You switch it out like that. Those would be independent. Okay, so that's the difference here between the two examples. The first example up here had the three vectors all lying in the same plane, so they're not independent. These had the three vectors not all lying in the same plane, and so they were independent. One last example before we end this video. I want to look at the polynomials of degree n or less, Pn, and look at the set 1, x, x squared, and so on up to xn. Remember, in Pn, the vectors are functions. In fact, they're polynomial functions of degree n or less. And my claim is that these how many are there? I guess there's n plus 1 of these functions, that these are independent. As in, look at what would happen if you took a linear combination. So I'm going to multiply this one by a1. No, actually, I think I'm doing multiplying by a0, a1, a2, all the way up to an. So I've got all those coefficients multiplied by all those things and then add them up. So I have a linear combination of these n plus 1 vectors, and I'm saying I want that equal to the 0 vector. Well, in Pn, the 0 vector is the constant function 0. It's you plug in any x you want, you're going to get 0 out, right? The graph is a horizontal line. Right? So the question now is, how can you take a0, a1, whatever, and get that to add up to the constant 0 function? Now, clearly, if you take all of those a's equal to 0, then you just have the 0 function. So that one works. Is there another way to do it? Well, if any one of those, for instance, if the a2 is not equal to 0, then this is a quadratic, or maybe more, but that quadratic term is going to make this thing go off to infinity. Right? And one of the things about adding polynomials is we only have a way of combining them as if they're like terms, right? I can't add together ax1 and ax2 and get them to cancel out somehow, right? It doesn't work that way. So there's other ways that we can prove, I mean, I'm just sort of reasoning through this, but I can prove that these all have to be 0. Because to say that this polynomial on the left is equal to the constant function 0, it means that any value of x I plug in, I should get 0 out. So since there's n plus 1 variables here, a0, a1, up to an, if I just plugged in n plus 1 different values of x, I could get n plus 1 equations in the variables a1 up to an, sorry, a0 up to an, and I could just solve with a big matrix. Right? The easiest one, I think, is just plug in x equals 0. If you plug in x equals 0, it tells you that a0 has to be equal to 0. But at least there's one of them that has to be 0. Then you just start plugging in other values of x, get a bunch of equations, solve it, and you can prove that they do, in fact, all have to be 0. We'll have another way in a little bit, a couple of videos later, called the Wronskian, and it will show us another way of thinking about functions as being independent. All right. Anyway, there's the notion of independence. In the next video, we'll look at some more examples and some theorems about independence.